All right, everyone. Welcome to the first colloquy of the semester. We have a really great lineup, and I'm happy to present Erika Hamden to kick us off. Dr. Hamden got her bachelor's from Harvard University. Then she went on to get a master's and PhD from Columbia University before heading to Caltech for a postdoc. University of Arizona was lucky enough to get her as faculty in 2018. And then in 2023, she became director of UASI, which she'll be talking about a bit. She was also recently appointed to the State of Arizona Space Commission by the governor for a 6-year term, and also recently had a book come out, Weird Science. And she is also the deputy PI of Aspera, which she'll also be talking about today, right?
Yes.
Okay, so please give a warm welcome to Dr. Hamden.
Thank you, guys. Thank you for having me. I'm honored to be at the first colloquium, and the room isn't full of lost students, so I feel like that's pretty good for the first week. So I'm going to talk about the Space Institute, give you guys a little bit of an overview of what we do and how we try to assist. And then I'm going to talk a little bit about in part of that, the process of space mission development. And then I'm going to talk about a mission that I've been involved in since its inception in 2019, Aspera, which is being integrated on the second floor of this building over in that direction, causing problems for the facilities people on a regular basis. Okay, so the Space Institute is part of what used to be RII, Research, Innovation, and Impact, and is now the Office of Research and Partnerships. And it was formed in around 2021. And the idea behind it was that the University of Arizona has been great at space sciences for a really long time. If you want to include ground-based observations, we've been doing it for over 100 years. A lot of that work was and is heavily dependent on individual personalities. Space mission development in general is long and arduous and super annoying, and you have to have the right type of person that is willing to do that even one time and then again and again. And so the Space Institute was started as a way to try to create more of a structure to support people who are interested in developing space missions and not just relying on individual faculty members who happen to be really interested in it. If those people leave, then no more space missions. So the Space Institute, we're trying to create more of a broad bench of people who can potentially be principal investigators, and also to just help support proposal development and different instrument development in general. So we've been working a lot on our branding. We go to conferences and have a little booth that we set up at different symposia and stuff, and people are always like, "Oh, Arizona, you guys do space things?" And my eyes pop out of my head when I hear that because we are the best in the world at space. So we have been a leader in space science funding for decades. We were recently surpassed in astronomy and astrophysics funding by Berkeley last year, but prior to that, we have been #1 since 1987. And we have the Space Institute did helped with a kind of report about the impact of space on the local economy. And so I want to teach all of you guys this so that when you talk to people, you can say it and they could be like, "Oh, wow." Space sciences generates a Super Bowl's worth of economic development for Southern Arizona every single year. We've never hosted a Super Bowl, and ideally we never will. And I say that because a lot of the focus of the university, depending on who's in charge of the university, they care more about athletics than anything else, but actually space is our business, and that's what we should be promoting. The space also generates a bunch of taxes for Arizona, and it drives the local economy in a really, I think, sustainable way where people get an incredible education here for a pretty decent price. And then if there are jobs for them in kind of the space economy, then they can stay in Tucson, they can stay in Arizona. So for the Space Commission that the state has stood up, we're still kind of getting started with it, but one of the parts that I really want to push is getting more support from the state for workforce development and for training for students. The University of Arizona is one of the only places on Earth where you can be a student and get space flight mission experience and then easily get a job instead of having to go out into the into the world where nobody wants to hire you. So a little more kind of just facts about what we have done. And this is the University of Arizona as a whole, not the Space Institute. We are like really meant to support the work that's done here at LPL and at Stewart and at OPSI. But the University of Arizona is the only US university that has contributed instruments to 3 great observatories, the NASA astrophysics flagships, basically. HST, CERTIF, which became Spitzer, and then JWST. We are the only university that has managed 3 solar system missions, Mars Phoenix, OSIRIS-REx, and now OSIRIS-APEX. We have the largest telescope orbiting another planet with Mars HiRISE, and we build the largest mirrors on Earth, limited only by, I think, like an underpass on the way to the highway. And also the only good reason to have a football stadium, in my opinion. Build mirrors underneath it. So UASI, we are trying to help support this like really long and incredible heritage in space missions. And sometimes, you know, I don't want to give the impression that UASI does this. We are just trying to help get money in order for you guys to do this. And so my goal as director of UASI is like, if I can help everybody win, what I want is for there to be an Arizona proposal to every single NASA opportunity and most NSF opportunities and probably other funders. But then I want us to win all of those things and then to have to like have so much money that we have a problem with hiring people. So we have a bunch of different kind of goals that we're trying to achieve. When I was interviewing for UASI director, they were like, oh, we want you to help, goal 1, generate sustainability from an expanded portfolio and continuous funding. So I interpreted that as helping people write big mission proposals because that's what I like doing. Then we want to help support new principal investigators. I'm really interested in that. We want to maintain engineering and technical talent. One of the sorry, I'm just moving the cursor. One of the challenges in having like big missions is then the missions end and then you have a bunch of incredibly well-trained people and you need them to stay in their jobs so that then when the next big mission comes along, they're still there. So keeping that talent. And then goal 4 is a new one that was sort of added on: advanced development, test, and operations facilities. And so when I interviewed, the focus was really about the mission development, helping with proposals, helping get the missions selected. And then when I took the job, they were like, oh, also you have 3 buildings that you're going to manage and all the people that work there. So at least from the proposal development side, we provide seed grants and proposal preparation support. And this is, I think, a really unique capability that we're very happy to be able to offer. So at most universities, if you were like, oh, I want to write a proposal to NASA for a CubeSat, your university might be like, well, you still have to teach 2 or 3 classes a semester. You have to like advise all your students. You have to do all this of your regular job. But what they don't usually do is give you money to work on the proposal. But UASI, we have money from the state that we use specifically for seed grants for proposal development. So if you have a concept for like an instrument and you want to propose it, we can help with a bunch of different like mission types. So things going from CubeSats all the way to, we supported a probe class proposal, which is $1 billion proposal that was not selected. We put it in a couple years ago. We can also help with instrument development and then international collaborations. And our requirements are that we want it to really be proposal focused. We want we want the output to be a mission proposal or a path to a mission proposal that's going to be $5 million or more. So what we really push for is people going after larger opportunities. The things are a little thin on the ground right now in terms of large opportunities, but this is a good time to kind of start thinking about concepts for later on when there will be more money, might be more money. So when I talk to people who want to put seed grants in, I always try to emphasize that like we want there to be some opportunity that you're proposing for. It's not just like a research seed grant where you're like, oh, I want to work on this project. Can you give me money to pay for it? The idea is that in 18 months, NASA will request proposals for like a small explorer program. And so if I want to put a proposal in, I will put in a seed grant request to UASI and say, okay, I need to pay 1 month of my summer salary. I need to pay 15% of a systems engineer. I need to pay 20% of a project manager. I need $10,000 to pay for graphics, things like that, which is all geared towards getting the proposal um, written, beautiful, and then eventually selected. And as part of that, we also try to do some proposal, like internal team reviews. And Walt, our chief scientist, will set up like a red team review or color team review to have people who aren't on your team read through your proposal and give you feedback for it. That process is actually, I think, one of the most important things that you can do in any document that you're writing and any type of proposal that you're submitting, is having uninterested third parties read it and tell you what is bad about it. And then you can fix it. So that way the reviewers at the end aren't the ones that are telling you what is bad about it. And instead they see all the good things. And I want to just emphasize this again, that we really want to help support you guys in thinking of mission ideas, looking for opportunities to propose to, and then making something that you're really going to be proud of. In my own experience writing proposals, so when I came here in 2018. In 2019, I submitted a small Explorer proposal. That was before UASI existed. It was a huge amount of work. It was super irritating. It was so irritating, actually, that I created an entire workshop that I run with NASA called the PI Launchpad to teach people how to do the mission proposals so that nobody is as irritated as I was in the process. So I spent 8 months working on this proposal. It was for a mission called Hyperion. It was not selected. It had a bunch of weaknesses, but I wanted to do it because I knew that the first time you put in a proposal like this, it's generally not selected, but you need to get past the first time in order to then have a credible proposal for the next time. And it was like an all-consuming kind of process, but actually it was the best thing that I'd ever made. I was so proud of that document, even if it didn't do as well as I wanted. Then I developed that proposal for the Medium Explorer opportunity, which was due in 2021. And then that proposal became the best thing that I had ever made. It is still the best thing I ever made, actually, until Aspera launches. And that had no major weakness. It was rated as category 1, which is usually selected, but it was not selected because that year there were 5 category 1 missions and they only picked 2. But so I love working on the proposals. I feel like you create this like really beautiful, almost a work of art that is, it's positive, and it's like thinking about like what could be possible in a better world. So I feel like I really like that experience of like thinking about possibility and not just about like the crummy ways that things are, but like how things can be. So for me, I realized like, oh, writing these proposals is like the art form that my brain wants to do. And you write something, you create it, and then you send it out into the world, and you can't control how people evaluate it or whether they like it or not, but you know, that's like the way it is with art. So that is a very long way to say that like at UASI, we want to support your large mission proposals, your path to a large mission proposal. We have a template that you can fill out and you can email me and I can send it to you and we can talk about it. We have an executive panel, which is composed of, I think it's 8 people, 6 to 8 people, who vote on the SEA grant requests. And we try to have the executive panel meet once a quarter. But we also take requests for seed grants outside of those meetings in like an asynchronous fashion. So we've had some success stories. As with all things, you put proposals in and most of them don't get selected. So you have to like play the numbers game where you just like keep putting them in and then some of them hit. So Aspera is the small sat that I'm going to talk about in a little bit. It's an Astrophysics Pioneers mission, which is a $20 million basically like standalone satellite. So this was selected just as UASI was getting started, and then UASI really helped us with the concept study report. So this basically we were funded to do a phase A, and UASI helped us with the phase A, and then we got funded to build the whole thing. And then we've had a bunch of other concepts that kind of span planetary science, earth science. We haven't done as much, or sorry, planetary science and astrophysics. We haven't done as much in earth science, although we are missing Jack Holt's Snow for Flow. We haven't expanded into heliophysics as much, but we'll get there. So we kind of, for the most part, it's on the small side because again, the big opportunities are not as frequent and the odds are just as challenging. but we are helping with OSIRIS Apex, the New Frontiers extended mission of OSIRIS-REx. We are working on another astrophysics pioneers concept that's called Pandora. We're doing the mission operations for Pandora. And then we have CATSAT, this entirely student-built and operated small satellite tech demonstration. The LEMS Artemis 3 seismometer, SHIMCO is a sounding rocket, and then WINS a TRL plasma probe, TRL advancement plasma probe. So we have a decent number of success stories. If you go like straight by the numbers, OSIRIS Apex like makes us look so great because it's such a large amount of money. But I think we're doing pretty well. And we also want to, this is something that we're working on getting better at, but we want to help with just like program implementation support. So it's one thing to win the proposal, have it be selected, and then have the mission come here. And then it's another thing to be able to deliver what you promised NASA you were going to do. So we have been building up our capability, and part of it is just me and the UASI team knowing enough people to say like, oh, you need a systems engineer, here's this person who has a little bit of time available, maybe you should talk to them about it. But we do at least have a decent understanding of the steps that are required for mission development, and we can help tell you what you need to find. Like maybe you need a project manager, you need engineers, you need some admin help for purchasing, for example, is like a whole job when you're building a spacecraft. And then for the proposal itself, as I said, Walt helps with all the review and oversight, internal like the proposal reviews, but then also like our own kind of progress assessments, and helping with formal review support, PDRs, CDRs, the concept study reports, the actual like products that you're giving to NASA. So in general, we just want to like be as helpful as we can. Another thing you might be curious or wondering about is, so if we help you with a proposal and you get the proposal, the university charges the indirect cost, and there's like a whole system set up for how the indirect cost flows from the university down to the PI potentially. And UASI, we do not take any of the indirect costs. So like we just want to help you, and we're not going to be like, oh, now you owe us a bunch of money when it gets selected. Tomas, the VP for research, his view is basically like we're providing this service, and it's not in exchange for anything. We just want to help. So the indirect cost and everything still flows normally as it would if you didn't work with us at all. But your proposal will be worse if you don't work with us. We also have facilities. As I said, there was a bait and switch in my hiring as director where I got saddled with these buildings. The buildings are actually great. They just take a bunch of psychic energy. So we have the Applied Research Building, the ARB. No one has yet donated enough money to us to get their name on it. But if you know anybody, let us know. So this is just north of Speedway, right near like the bike underpass that goes under Speedway at Mountain. And we have a bunch of really beautiful, the building itself is beautiful. The architects wanted it to be inspired by a bunch of space-related things. So the exterior is partially inspired by the International Space Station. The like vertical windows and like kind of fins are meant to mimic the solar panel arrays on the space station. And then on the inside, some of the interior structures are supposed to like be reminiscent of the rocket gantry that you would walk up if you were gonna launch into space. But it has a fabulous and all very new, and in some sense, some places are unoccupied. Clean room facilities, really nice lab spaces. We have an anechoic chamber. So part of the idea behind the building overall is if you write your proposal, USI helps you, it gets selected, and then you need a place to actually build the mission. So you can put your components together in the clean room spaces. We have a high bay, and then we have a bunch of environmental test facilities. So before you launch something, you want to do an anechoic chamber test where you verify that different parts of your instrument or spacecraft aren't going to interfere with each other, and you'll be able to talk to it. You want to put it through a vibe testing. So we have a large vibe table and then a very tiny one, and a couple of other kind of shock test setups. And we had recently hired an engineer who basically just helps run these systems. So you are mimicking the load that your instrument or your mission is going to experience during launch and any other events that might be happening. And this is the key part of certifying that you're ready for launch. We have a thermal vac chamber. The building was actually built around the thermal vac chamber. It's the largest thermal vac chamber at a university in America. You can drive an Escalade into it. And it's actually the TVAC chamber was originally used by Grumman in the 80s to test space suits, and then they mothballed it in the 90s, and then they were trying to sell it. And so briefly it was on eBay for $300,000. But we didn't buy it from eBay. We bought it like through a broker, and it actually cost more to move it here from New Jersey, where it was, than it cost than to like physically buy it. They put it, they put the like concrete slab, put it down, and then built the rest of the building around it because it's so huge. So it has this massive door. I always love these because I feel like, oh, this is a perfect like James Bond villain chamber. You like stick someone in the vacuum chamber. But it has a series of clean rooms. So you start out in the high bay, and then you can move into like a dirty clean room, and then a cleaner clean room, and then the antechamber is a clean room, and then you put it into the thermal vac chamber, close the door. It is lined with a bunch of infrared lamps, and we have liquid nitrogen cooling, so you can basically mimic the environment that your instrument or your spacecraft is going to be under when it goes out into space. And so you can tell whether one of your components is not actually space rated and doesn't work, or doesn't radiate, or doesn't like deal with its heat load correctly. So this is a really great facility. There's smaller TVAC chambers in the building, and there's other TVAC chambers on campus for smaller things, but for a large test article, this is really like a very unique capability. We also have a mission operations center and the capability of doing data archiving. So for Pandora, we are running mission operations, which basically means the Pandora science team tells us we want to look at these targets at these times, and then we actually send the commands to the spacecraft and then get the data back and then distribute it to the team. So this is an interesting kind of capability for a university. Most of the time, if you're doing mission operations, you'll go with your spacecraft provider, or maybe a NASA center will do it, and they will charge you an arm and a leg for it. But we can do it even under very adverse circumstances. We are testing the kind of code architecture that we built for Pandora, the first mission that we're doing mission operations for. And the spacecraft provider is incredibly mad that we are doing it because we underbid them, and they like wanted the money for it. And so they've been acting like the worst bratty partners ever. And because I believe very strongly in naming names, it's Blue Canyon. You should never deal with them. They like have done everything they can to keep us from actually communicating with the spacecraft, but we have such a good team that we were able to still communicate with the spacecraft, even though they wouldn't tell us anything about its settings. So yeah, don't work with Blue Canyon, but we are happy to do mission operations. And then we have two big high bays. So the window here, this is the mission operations center, and then you can actually look onto the two high bays. And right now, one of them has the Magnum telescope, which is a telescope that used to be on Hawaii. We're refurbishing it, and then it will go up Mount Lemmon. But the idea is like you can build your instrument in the clean room, you can put everything together in the high bay, then you send it to TVAC testing, you send it to anechoic testing, you send it to the vibe testing, and then you ship it out to get launched, and then you can operate it from Mission Operations Center. So it's like a full service kind of facility. We also have a building down towards the airport, the Mission Integration Lab, which is really designed for balloon payloads. So it has a crane, and a crane that goes out the door, so you can like move your balloon payload out and look at the sky. It has a really nice piece of art also. And then the third building we have is the Grand Challenges Research Building. This is much more of a standard kind of lab building, and there's a bunch of different departments. Some of the floors are OPSI, some of them are other things. This is most recently become the office of the home of the Office of Research and Partnerships. So they were in the administrative building, now they're on the fifth floor of this building. It just opened. It's really nice. There's like a really big conference space on the first floor that some of you may have been in, with like one really huge room and then two kind of smaller rooms. Yeah, the building itself is a pretty standard building, but we help with just kind of the facilities and the IT support in the building. Okay, so I think for the most part, that's what I wanted to cover about what UASI can do. I wanted to touch just briefly on the project that I've been working on since 2019, called Aspera, the small sat mission that I had mentioned. And in my own research as an astrophysicist, I'm very interested in like the precursor of an object. So when you look out into space, there's like planets, there's stars, there's galaxies. And I like all of those things, but I'm not as interested in like the galaxy. I'm interested in the stuff that goes into the galaxy. Like how did the galaxy form? How does the galaxy get fed? Why do galaxies look the way they do? And how do they kind of interact with their environments? How do they keep forming stars? Where is the hydrogen coming from? And like what happens when that hydrogen is cut off? And how galaxies end up becoming like elliptical galaxies where they are not really forming new stars. So this is a like artist rendering. It's actually a compilation of a bunch of different real galaxies to illustrate the sort of environment of a spiral galaxy. So I think Mark Marley told me once that planetary scientists are either into atmospheres or into solid objects. You're like a surface person or you're an atmosphere person. So I thought to appeal to all of you guys, I would be like, this is the atmosphere of a galaxy. So now you get it. So in this view, the galaxy itself is like just in the middle here, but it actually exists within this much larger halo. There's the dark matter halo, but there's also a bunch of other baryons in the halo. So it's mostly hydrogen, but some other metals. Everything that isn't hydrogen or helium, astronomers call metals. So I apologize, but I mean like oxygen and carbon. And so some of it comes from the galaxy itself. The galaxy forms stars. Those stars like explode in really big outflows, like what's shown up here in this corner. And those outflows can sometimes escape from the halo of the galaxy and like pollute farther out into the intergalactic medium. But then eventually a lot of it will just fall back down. It doesn't actually have enough energy to escape the gravitational well of the galaxy. It just ends up like in a fountain. It comes up and then goes down. There's also satellite accretion where you have minor satellite galaxies which have their own hydrogen and they get eaten by the larger galaxy. And then what this doesn't exactly show is like there's accretion that's from pristine gas from the Big Bang that has been floating out in intergalactic space that eventually makes its way into the galaxy. So these galaxies exist in like a really complicated multi-phase environment. And right now, the way that we deal with them is in what I feel like is a terrible way, but it's actually the only way that works. It's using what are called absorption line observations. And so this is actually similar to like occultations where you're trying to probe the atmosphere of a planet, and so you see a star go behind it, and it's like good but not as great as if you could just measure it directly. So we have quasars, these super bright distant galaxies that provide a background source, and then you're looking at the impact of a foreground galaxy's halo on the spectrum of the background source. So this this kind of work has been done since the installation of the cosmic origin spectrograph on Hubble. I think it was in 2009. So you can probe like this single line of sight and you can measure like, oh, is there hydrogen there? Is there carbon there? Is there oxygen there? And we find that there's actually pretty decent columns of material. You can kind of do these individual pinpoints and then get figures that look like this. So this is showing basically the abundance of whatever particular element is listed here, or ionic state, and then the distance from the center of the galaxy in kiloparsecs. And so each of these points represents a different galaxy. Sometimes we will observe a bunch of galaxies that are like similar mass, similar type of galaxy, and then you shove all of those individual points together. But this is like a statistical galaxy. So part of the shortcomings of this is like there is no single galaxy where you could be like, hey, this is the abundance of hydrogen with distance from the center of the galaxy, because for any one galaxy you just have like one position. So that's one of the drawbacks of the absorption line studies. But what they do tell us is like these halos have a bunch of hydrogen, they have magnesium. The magnesium might be concentrated along the minor axis because it's primarily associated with exploding supernovae, and They have some carbon in different carbon 2 and carbon 4, silicon, oxygen. So the missions that I've worked on have all been tackling this problem from different wavelengths and different kind of perspectives. So there was a mission that was a UV balloon boring telescope called Fireball that was looking for Lyman alpha emissions. So we're looking actually for hydrogen. Another mission that is in development that I'm going to propose to the Small Explorer opportunity in 2027. We're looking at carbon 4. Aspera is looking at oxygen 6. And then I'm working on a concept to propose to the APRA program, which is kind of smaller balloon suborbital payloads that we want to look at magnesium 2. And you can look at all these different things, and they each tell you something slightly different about the gas that you'd be measuring. So oxygen 6 is typically like warm hot gas, which is 10 to the 6 Kelvin. It's not as hot as things which emit in the X-ray. But the overall reason is because like we don't actually know where most of the gas is in a galaxy. Um, when we measure, that was awesome. When we when we like look at galaxies, one of the key questions about them is actually like how much material is there? How much does the galaxy weigh, and where is all of the where are all of the baryons distributed? And so this graph is a little bit old, but actually there hasn't been a lot of data to inform this since 2014, so it's still relevant. The fractional percent of baryon budget, only a tiny amount of it is actually in the disk, in the stars, and the molecular clouds of the galaxy that like we think of as the galaxy. So the solid regions are things that we've observed, and then the kind of dashed area is what we think it should be, but we actually haven't gotten observational evidence of it. So the disk, colder CGM gas, the circumgalactic medium, is the atmosphere. Warm hot CGM gas, and then very hot CGM gas. So the hot CGM gas is traced by X-rays. Warm hot is mostly in the UV. Cool CGM is in the radio and some other wavelengths. But so what's interesting is that the component that we're trying to observe with Aspera, the warm hot CGM, is actually maybe larger by mass than the disk of the galaxy, and yet we've observed barely any of it. And so for a total kind of canonical galaxy halo, we've observed maybe a third of the total baryons that we think should be in the galaxy. Astronomers are super self-absorbed, so we refer to this as the missing baryon problem, which I really hate because like they're not missing. They're there, we just haven't seen them yet. So the goal with Aspera is basically to map and observe this warm hot, also known as coronal gas. And this has been a problem for a long time. So Lyman Spitzer wrote this in 1976. The Spitzer Space Telescope was named after him. While the hot gas observed with Copernicus is very similar to the extended corona suggested nearly 20 years ago, the origin and spatial distribution of the observed coronal gas is not at all certain. So with Aspera, we're hoping to be able to solve this now almost 50-year problem, 70-year problem, by basically looking directly for the faint coronal gas. And the challenges with it are that it's really faint. It emits in the far UV for galaxies that are nearby. It's actually in the extreme UV at 1032 angstroms. And we think that it is filamentary. If you remember the plots of kind of the emission or the abundances versus radius, like you have no information about how this is distributed around the galaxy itself. You could just assume that it looks like this, where there's like, oh, there's this big halo. Maybe it's like pretty even. But we don't actually think that's the case. We have simulations that indicate that it could be filamentary. And you can imagine a situation where if you have a absorption line and you point it here, you get nothing. If your background quasar happens to be right here, you would detect no oxygen 6. But if your background quasar is here, then you would get oxygen 6 absorption. So if you're doing these like pinpoint observations, you could just be really unlucky and not find something, even though this galaxy halo might have a ton of emission. So this is a simulation. The galaxy is in the center. We've just removed it because it's way brighter than everything else. So that's why it looks like a long hamburger. And this simulation suggests that the morphology of this oxygen 6 should be very filamentary. and not really like a diffuse kind of form filling, um, filling up the halo entirely. And the surface brightness, the expectation that we have is actually that it's really, really faint. So we observe our targets for like weeks at a time because they're so faint. So the Aspera mission is basically a way for the first time to like do a mapping of about 6 nearby galaxies in oxygen 6 to look for that emission directly and to make like a 2D map of it. So we are anticipating launching in 2026. 9 months of operations. One of the great things about this, because it's a small program, is that every single one of my grad students has been involved in it, and there have been, I think, over 30 undergrads that have worked on it. So some of them doing software, some of them doing hardware. It's been fantastic as a student training vehicle, even if it never does anything. Although it will, it's going to be awesome. But we did get an email from Doge a couple months ago that was like, what science would you be able to do if we didn't launch it into space? Because I am incapable of like not saying exactly how I feel. I didn't answer that email. Carlos, the PI, did. We were like, nothing. You would have wasted $20 million. So we are getting launched in 2026, and the goals are basically to kind of understand some of that cycle that I showed you in the artist rendering of how baryons move in and out of galaxies and what they do when they're in the halo. So we have 3 science objectives. First, just understanding how prevalent is the oxygen 6 emission around our target galaxies. Then determining the spatial distribution for some of those galaxies that seem like good targets. We'll do actual 2D maps of them. And then lastly, to try and understand how the gas is moving once you've observed where it is. So in order to do that, we have a spectrograph that will give us both the position and then the motion of the gas. So the team, Carlos Vargas is the PI. I'm the deputy PI. We have a great team of people from mostly from the University of Arizona. One of the unique things about this is like we are managing the mission, we're building the instrument, we're doing the science operations. The only thing that we are not doing at the University of Arizona is the spacecraft, which we purchased from SFL, a much better partner than Blue Canyon. And a few other people are not shown on here, but one thing that I like to talk about with this is this actually started as a astrophysics small sat studies proposal, which was an opportunity that NASA offered in 2019. I think only one time, and it was for they would give you like not even that much money, a couple $100,000 for a concept study report or like a mission concept. So the proposal itself was for an imager to look at oxygen 6, but it was pretty poorly conceived, and we weren't selected. And Carlos said he wanted to reformulate it for a Pioneers mission. This was the first year that NASA was offering Pioneers as a proposal opportunity. So we submitted it in October of 2020. I had mentioned way at the beginning that I had worked on I had submitted a small Explorer proposal called Hyperion that didn't get selected. But Carlos and I, and a bunch of other members of the team had worked on Hyperion, put it in 2019. In March of 2020, when everything was shutting down, that's when I got the call from NASA that it wasn't selected. And so we immediately started working on Aspera because we had learned how to do these big proposals, how to like put together all the components, how to make it look nice, how to make it compelling to the reader. And so we were selected in the first round of Pioneers selections, which was great because we didn't think it was going to get picked. And so now we're almost in the last phase before launch. We still have to send it to the spacecraft provider to get integrated. So once it's up, it's actually I'm going to switch these around. So it is a Roland circle spectrograph. So it's actually almost exactly the same as the UV spectrographs that are on the missions to the outer planets. All of those are Roland circle spectrographs. So you have an aperture, an off-axis parabola primary mirror. There is a slit here, and then the light passes through the slit, hits a toroidal grating, and then goes to a microchannel plate. So this is one channel. Off-axis parabola, the grating, and the microchannel plate, and we have 2 channels that share a microchannel plate. The spectrograph resolution is about 2000, 45 arc second spatial resolution, and the slit itself is 1 degree long, so it's a pretty long slit. And we're using all TRL6 technologies, thank goodness, because it is challenging enough to like get everything to work than to also try and do additional technology development. Um, and the kind of observing strategy is, we have this simulation of a galaxy. We've scaled it to what we think is the intensity that, from a few other emission observations, what the intensity that we think we should be able to, the galaxy should have. And then basically we will step across the galaxy and build up over time. This little animation is from when there were 4 channels and we had to do descope down to 2. But basically you just sit on different positions and then build it up to make a 2D map. So each of the kind of lines across is 2 days worth of exposure time. The instrument itself is very tiny. It's like this big, the size of like a mini fridge. And the 2 primary mirrors are 4 by 6 centimeters. So they are teeny tiny. If you contrast that with like JWST, this is like a tiny little thing. But one of the things that I think people underestimate about small satellites is you are trading the aperture for time. So if you have the time to stare at something, you don't need to have a giant telescope. You just need the time and you need a detector type that kind of allows you to build up the signal to noise. And so the kind of mission design is we have a 6-month science mission. We have 10 targets. The extended originally it was going to be a 9-month science mission. We don't have a ton of money, so we've made it 6 months because that will still meet our requirements. We're hoping to operate for longer. We're going to be at 600 kilometers of sun synchronous orbit. And then this is our completed bus, which is sitting at SFL waiting for us to send them the instrument. We're getting launched by Rocket Lab on an Electron rocket in 2026 from New Zealand, which will be really fun. And we have been working on the mission operations with Ascending Node Technologies, ANT, which is a local company that has really been fantastic. We've had really great partners, and that's actually, I think, one of the most important things about missions overall is like you have to work with people that you like working with because you're going to talk to them every single day. And there's going to be some really annoying times, and so you need to trust and believe in the people that you're working with. Then we've also had 37 students that have been trained on flight hardware, which is really incredible. A bunch of graduate students. I think only about 6 of these are graduate students. Most of them are undergraduates, which I'm really proud of. The undergrads worked with ANT on the software. So there was a bunch of software development, but then also we've had undergrads in the lab. And then a bunch of them now, because we've been doing this since 2021, now a bunch of them are graduating or graduated and got jobs, which is really annoying because now we have to train new people, or they move to graduate school. And as a faculty member, I know that I am happy that they are succeeding, and it's great, but it makes me sad because then they leave. So one thing that I think is really great is like Aspera is going to do really transformational science, solve this 50-year-old problem, but also has trained a ton of new scientists and engineers. And then we're actually doing the integration right now. So this is a little bit of like a payload status. We're using Walt's lab on the 2nd floor. Walt's is the best. So this is the actual like instrument itself. It's pretty small. Here are people for scale. There's no banana in this. Sorry. So these two like rectangles here are that's the front baffling. There's a bunch of baffling that isn't installed. And then these two here are where the primary mirrors are. We were doing optical alignment using a CGH, a computer generated hologram. I love the CGH, and it gives us really precise alignment to fit within our tolerances in a pretty straightforward manner. So this is our current schedule. I got the systems engineer to send me this morning, so it is very updated. We had originally wanted to ship everything by the end of, excuse me, by the end of the summer, but we had a problem with our high voltage power supply, where the 2 flight versions that we made had a couple of components that were incorrectly potted, and so when you put them in a vacuum, there's like trapped air bubbles and you get arcing. The detector we're using is a microchannel plate, so it needs a high voltage power supply. I strongly recommend that if you to not use microchannel plates if you can, because they are so difficult to deal with. Just get a CCD or CMOS detector. It's way better. Anyway, we have solved that problem, and so now we are here, 2 days away from finalizing our microchannel plate alignment, the actual detector alignment. Everything else is aligned. We're going to do full system staking at the end of September. Some initial vibe of just the instrument, or the environmental testing of the instrument, TVAC vibe, and then we ship it to SFL. We have about a month of margin, and then down here is our planned 2026 spacecraft integration, flight ready in July, and then launch ready on August 15th, 2026 from New Zealand, which will be really great. So I'm really happy to see this, because I remember when Aspera was just like Carlos's idea. He talked to a few faculty members, not here, but faculty members at other places, and said like, oh, I have this idea for a small sat. And all of them were like, that's never going to work. And all of them were wrong. So one of the things I want you guys to leave with about space mission development is that really you have to ignore everybody that tells you that it's not a good idea and find out for yourself if it's a good idea or not. One of the reasons why this mission has been possible is because in the late 2000s, NASA decided to invest in ultraviolet technology. The UV is not super useful on the surface of the Earth, and so doesn't get the same technology development efforts that like infrared technology does or X-ray technology does. But so in the UV, in the last 15 years, there's been a huge increase in the performance of mirror coatings, of the actual mirror surface is more reflective. The gratings have gotten better, detectors have gotten better. My kind of technology specialty is UV detectors, silicon detectors, so I'm happy to talk about those at any time with anybody. I try not to harass people on the street about them, but the other thing that is really amazing is that it has never been easier to get something into space than it is now. The size, like I remember when you couldn't get a spacecraft for like less than $70 million, and now you can buy them for pretty cheap, depending on what size you want. This is the list of orbital launches by year by country, and like this starts to look like an exponential curve. China is launching a lot more things into space. The US is launching more of them as well, even though I actually think this color looks more like South Korea than the United States, but I didn't make this plot. And it's never been busier in orbit than it is now. There's a huge number of Starlinks. Most things in orbit that are operating are actually SpaceX. There's other, the US is like here. But so I don't actually like how many satellites are in orbit, but it is really easy to hitch a ride on one of them to get your thing, at least into low Earth orbit. And it's a lot cheaper to build a spacecraft than it ever used to be. And I show this partly just to kind of urge a little bit of creativity. I know that with planetary science, things are not the same as astrophysics, but this is a figure showing total exposure time and then the like surface brightness that you can reach in that exposure time for a variety of mission concepts or mission ideas. So LUVOIR was a concept basically which turned into the Habitable Worlds Observatory, NASA's next flagship for the 2040s. CDIS was a 1 meter probe mission concept. FUSE was a UV telescope that launched in the 90s that actually Aspera uses the optical design of. It was the size of a school bus. And then Aspera is the blue line, again, this big, a 4 by 6 centimeter aperture. And Aspera gets better sensitivity than all of these because it has massive resolution elements. But the small satellite, like if you have a well-posed question, you can answer it with a small satellite. You don't need to wait for a flagship mission. So I show this to make the people who are really into flagships mad, although I do love a flagship. But I think there are people that I've talked to who say like, oh, you have to wait for a flagship to do things. And that's not correct. You don't have to wait for anything. You can come up with your own way of answering something. And just to give some view of the relative collecting area. So this is one of the concepts for LUVOIR, a different concept. I think it was like 15 meters, 8 meters, CDIS, the FUSE telescope, and then I think I enlarged the Aspera one by like a factor of 100 because it's so tiny that you wouldn't be able to see it. So small satellites can be really powerful if you do them in the right way. They're also a great way to work your way up into big missions. If you are the PI of a tiny thing, you're the PI of an instrument concept, and you show that you can do the management part, you can like deliver the capability that you say you're going to deliver, then NASA will be like, oh, this person is in a very small group of people that we would trust to build something to go to the outer solar system. We know that it will make it and do the work that it's supposed to do. So mission development, how to design a space mission is really a long-term project that is mostly about tenacity and then only slightly about like technical ability, because you just hire people to do the optics and all the other parts. The thing that is really important is to have a good science question that you want to address, and be willing to keep going, even if NASA tells you no a bunch of times. So with that, I'm going to end. I want to just highlight some people to contact at UASI, going back to the beginning of this talk. If you want to talk about science, proposing things, reviews, talk to Walt. He's right here. You guys all know him. Tom McMahon is our program manager. He deals with engineering, management, and like kind of the building resources, other resources that we have. You can, of course, always talk to me, but I didn't put my email address on here. It's hamden@arizona.edu. And I'm happy to take any questions. Thank you so much.
Questions? Yeah, Ty?
We have the audio redone over the summer.
That's right off the
I don't think you.
Oh, okay.
That's great news. I'm happy to check it out.
Mhm.
I have a question about the entry point for developing movies with the Space Institute. And so the idea that you could arrive at your door with an idea of something that might be suitable to a space mission, and you could help us develop that and maybe find a program that would be applying to, or should we have a target program in mind that we think our idea fits into before approaching you all?
So I think you could approach me and Walt with an idea, and we would try to figure out where it might fit. We wouldn't want to send it to the executive panel until we have like a clear target and a little more detail. But you don't have to approach us with like, here's my point design. You can say like, oh, this is the thing I've been thinking about. I don't know if it will work. I think it's better if you come to us in earlier stages, and we can help. Between me and Walt and the other people, we have a huge experience writing proposals. Whether they've all Walt and I have both gotten category 1 proposals that were not selected, so we're really good at writing excellent proposals. Beyond that, we can't help you. But I think for me, I also run a workshop that's called the PI Launchpad, which is kind of to help people that are in that state where you have a science question, but you don't actually know what to do with it. So there's a lot of material online that if you Google like PI Launchpad NASA, we have archived everything, all the presentations and stuff. So you can talk to us, you can look up that. But I think the main thing is if it's grounded in really good science, then we want to help you to figure out how to kind of get it to an actual reality. Another question. Oh, question up there.
Thank you. That was a fantastic talk. Really cool work y'all are doing. I'm curious about, so it's fantastic the number of undergraduate and graduate students still supported through the missions that you're working on through UASI. Is there a specific channel for folks who are seeking out like post-bac or work opportunities through UASI? I talked to a lot of undergrads about seeking that out in a time where getting into grad school is harder than ever.
Yeah. So we don't have a ton of staff for UASI. We can like try to help connect you of like, oh, we know of this project or this mission that might need people. So we try to connect people. We don't really have a lot of staff positions.
Gotcha, that makes
Yeah.
sense. Cool. Thanks.
I will say that everyone always needs a systems engineer. Like, get a master's in systems engineering and you'll be unstoppable. You have another question?
Yeah, let's just follow up about the PI Launchpad.
Yeah.
If you could say a little bit about what career stage or stages that's targeted at.
Yeah, so the PI Launchpad, we don't filter on career stage. The requirements are that you have not yet put in a big proposal as like the PI, deputy PI project scientist, and also that you've submitted some type of research proposal. So it could be to NASA, it could be to the NSF. We have accepted people who are grad students. We haven't, like, we've accepted senior grad students. There's usually a few every time we run it. And we've also had people who are like senior faculty who have just never done mission stuff. So we kind of take anybody. The application itself is 5 questions. The first one is about your mission concept, and we just check that it is relevant to SMD and it requires a spaceflight investigation. We don't really evaluate the science. And then all the other questions are about leadership, being on a team, decision making, and the questions are designed. So I like wanted to help people that were like me, and I want them to know that other people are also people without me having to teach them that. So the questions are designed to kind of find people who already think that. People really tell on themselves in the responses. I like read every single one. But so we don't, in all of that, we're not looking whether you're a grad student or you're have a PhD or not. And this past time we had a grad student from the U of A that attended. It was like 2 weeks ago at Ames. We do it every 2 years, so the next one hopefully will be 2027. Yeah. If someone else wanted to run it, that would be awesome, because I run a program called the PI Launchpad, and I'm technically not the PI of a space mission.
That's a question.
Yeah.
In the beginning of your talk, you dropped the heliophysics. So what about heliophysics?
Yeah, so we just haven't had any when I was talking about our success stories, yeah, we haven't had any PIs approach us with like heliophysics concepts, is what I would say. So we are very wins. Oh yeah. Heliophysics. But I would say that I mean I don't know, Walt, if you agree, but I feel like that's an area where we could really do more.
We could.
Yeah. And it seems like, especially in the current NASA climate, there's heliophysics feels like it's a little bit safer than other parts of the science mission directorate, because there's direct implications for like satellite health and stuff. Yeah.
So we have to go with moment. We have to go through the same procedure with you.
Yeah. Yes. Yeah. We are agnostic to science as long as it's happening in space. And no one has yet argued that like things that happen on Earth are happening in space, even though technically that's true. But if your thing is going to space or is going to look at space, then we will support it. Because we have also helped some ground-based stuff, things for like first light instruments for GMT and a few things like that we've supported.
Lost a science question too.
You should have a meeting with me today.
Red plot from Jason Tumlinson. What was going on with Oxygen 7? It's in the lower right, and it was just.
I was just so sad. Look at this. Terrible. So Oxygen 7, there's no detections, and so this is like the sensitivity limit. But you really need an X-ray telescope. That's mostly what's happening there. But Carlos has this idea that once we get so oxygen, there's many different ionization states. So we're doing oxygen 6, but you could imagine like a whole set of telescopes, and each one is for a different state of oxygen, and then you would get like a full, beautiful map of all the temperatures, all the densities.
Any other questions? Okay, let's thank our speaker.